Welcome everyone for High Performance Computing, Advanced Scientific Computing. Today we have the short lecture 15, Terrestrial Systems and Climate, which is one of our final lectures in the course, basically summarizing a lot of concepts we have seen in the initial part, which was really the first part of this course, which was about MPI, OpenMP, the difference between CPUs, GPUs, domain decompositions, and lots of conceptual topics that we then in the second part of these courses, starting essentially from lecture 10 up to 15 now, basically have looked up what we can use from that basically in all the different sciences. Again, before we go here in the terrestrial systems and the climate simulations, let us just review what we had the last time. And this was really diving into the tiny world of the few and of the nanometers with atoms that really basically consist of so-called electron clouds, if you know a little bit about chemistry. And there are different ways how you use that for simulations. Some simulations, if you have seen, which are a bit more rough, if you want treat this all as one atom, and then you basically compute all the interactions with the different atoms that form molecules and so forth, or you really take the atom as is with the different, electrons, neutrons, and so on. So these are already different schools, so to speak, how you compute all of this. And you can imagine the more detailed you go in, having even the core of the atoms considered, the more computing you require. Now, in molecular systems, obviously, forming different atoms to something bigger is the goal, and to understand then how the larger system react. You have seen the Euclid Salon idea in the end of this lecture, where we have understood that in the end, this ice block that is, then happily wandering around in this Euclid Salon and is swimming there, in the end is just a bunch of atoms, but of course, differently held together with a crystalline structure, which is ice. And then over time was melting and coming into the problem that the atoms didn't really stick together anymore in this crystalline ice form, and formed another part, of course, which was then H2O, as you know, with the water molecules and so on. So we see here, this is exactly the goal of basically these systems to analyze, to simulate. And obviously, this could be now in very many different sciences areas. So, because many of the elements we see today in engineering is basically based on molecular systems to understand really what's happening. And here's another example that I showed you, which is basically an interesting and well-known topic, which is drug design, right? In order to form a new drug that should be on the market, you have some target where you think you have a ligand that is able to dock. And if it's docking and you have maybe found a new drug where you think you're happy, there are so-called force fields that you see here between the different atoms and molecule parts, and of the larger protein that we then had. And if you remember, the protein was really doing a function in the body. So it's a very important cornerstone. Hence, we want to dock to it. And however, the problem of these force fields is then in the end that they drag the position again out of the docking, or basically don't just temporarily. And that is exactly the goal of doing molecular dynamic simulations later. So you would have firstly this idea of using, docking, and then once you docked, you would basically go to something which you see here, which is much more molecular dynamics, to really see in an iterative loop, almost like your assignment 3, right? What I said in many of the office hours now, you need an overarching loop that really moves basically time step by time step your water, your boats, your fishes. And in the same way, we compute here time step by time step the new position of atoms based on the force field interactions. And of course, this is based on known physical laws and numerical methods. And then you see the key essence as we go over time. And we have seen that the timescales of this is, of course, an interesting part in molecular mechanics, and all of these elements have different time scales, different spatial scales. And with this, you basically simulate a lot of time of the supercomputer, but actually what you really simulated could be just in the nanoseconds, maybe or so, on the atomistic level. So here we saw already a requirement to really need more computing overall, moving to exascale systems in the future, because here we have seen that a complete atomistic simulation in many cases is completely not possible. You have to abstract from different perspectives. Now, when you look, however, how the new technologies come and help there, we have seen a little bit a kind of, view that basically all the different packages and libraries that we have for these systems, like Ember for molecular dynamics here, NAMD, and GROMACS, these are all different packages which have been used by many applications in the past, as basically in the future for these simulations. They are basically ported now out to GPUs, which is mostly CUDA, of course, and NVIDIA GPUs. And what we also will learn basically when we look at some job descriptions here, that AMD is of course around of providing now GPUs. So basically with this and with Intel GPUs on the market, more and more GPU heterogeneity, we can expect that there's of course much more jobs to port all of these different libraries that you see here, not only to CUDA and NVIDIA GPUs, but also to ROC toolkits for AMD and so forth. So it's a continuous development of these libraries, but of course with this, they also perform better and better, that you see also from the efficiency perspective here, here and there in these different elements. So putting this on a larger scale, I also made a brief excursus in the infrastructures that have been around, like grid infrastructures in the past, where you then have iterative here, this idea of docking with a ligand, and basically the idea then of finding targets for drugs. And you can do this on a larger scale, really on HTC, because the docking process over itself is not so computing intensive and can be really scaled out and not interacting with itself, right? You have different targets, different ligands, so this can be embarrassingly parallel. And if you have once this intermediate results, you store it to disks, you think, okay, you have found a potential drug, then you basically do the, Ember, the dynamics over time, and you will find that many of these dockings are actually junk and has to be removed. And some of them are really hits. And this is, of course, something where molecular dynamics simulations require really HPC resources, because they really have to have the particle interaction here on the atomistic level with the force fields as I described. So here you really need, the interconnectivity of all these different cores, because the force fields are really interacting heavily with each other. And the more HPC resources you have, of course, the bigger the atomistic representation you can have. Of course, we saw also a little bit also in earlier lectures, one should not forget the data in between. So parallel file systems, a bit illustrated here with this cutting off, is of course also an important ingredient to high performance. And this is really just a very short intro to molecular systems. There's a big world in material sciences around this, with lots of different subdisciplines, as I was alluding to the last time. An interesting world. And if you are interested here in the University of Iceland, the two really experts which are driving our computational chemistry lab is really Egil Skulason and Hannes Jonsson. So if you're interested in doing, research, or basically want to be part of this particular community, it makes sense to also talk to them or take some courses that they offer. Because obviously, I cannot present the whole details on all these different, let's say, scientific disciplines that you've seen here. Obviously, machine learning is the field of my own, so I could extend there a little bit with my PhD students. And then a couple of those have also, let's say, introduced already some other disciplines where HPC makes sense. And we can go on and look, for instance, at the praise report that I was sharing also earlier, that there are much more communities. In the same way, today I will dive very briefly into the terrestrial systems, a very interesting player for high performance computing, if not one of the major drivers together with neurosciences. Here we really face enormous complexity to represent our Earth, to build a digital twin of our Earth, of all those chemical processes and that we see there. And in the end, we also know that, of course, with climate long-term studies, how it works with our climate change is also a very tremendous way of research where lots of things have to be done. So here again, the note, of course, if you want to be an Earth scientist in terms of numerical simulations with terrestrial systems, you need to have some other Earth science courses, really. And here we really focus a bit on the HPC aspects on it. And of course, I pick here one example, which particularly I pick because it shows a coupling very well. Because the more you want to be realistic in terms of simulating and modeling terrestrial systems, you need different physical processes to interact with each other. And this interaction needs to be coupled with so-called couplers. And one example is here the OASIS coupler that is actually used to couple here 3 different models in the earth sciences domain that we had already in some of the lectures shortly introduced, but I will come to that back and how it actually works together. Then the second part of the course is a little bit looking into what we know already from Weatherstoban every day, right? So numerical weather prediction, NWP, so how is that working? And with this also reflecting on a little bit what Reza and other lectures already highlighted, the role of change in this partial differential equations over time, why we're using this actually to come and basically have numerical methods there in this context. We will look at some particular code, weather research forecast, which in one way is a little bit interesting perhaps for you because it's often used in Fortran, right? So this is a general theme in scientific computing. You still have some Fortran codes around, which is interesting because many people, of course, think about Python now and think already C is very old. Now think about that Fortran developers are also not many around. So this is definitely a community where many Fortran codes still exists, and of course where a shortage of application developers exists as well. So if you have interest in Fortran development, I'm sure you find good jobs in basically in this terrestrial system and climate areas. Just finishing there a little bit with the parallel net CDF file format, again alluding to the point that HPC also lives from parallel I/O, concurrent access to files, which makes a difference, as we have already seen in the MPI BLAST application, for instance, for the sequence or gene sequence search, really. With this, you have the learning outcomes again of really important parts of domain decomposition. We will basically crunch down the terrestrial domains again. We will have a look on how we can do their domain decomposition. And this will be many, many terms you already heard about, creating halo layers. So you will see that again and again, of course, we will make links to MPI, OpenMP, kind of shared memory, distributed memory processing combined then with the idea of this hybrid programming, and then also think about different domain decompositions, all what you already learned. So of course, this is also one of the idea here to see that the conceptual parts that we had in the first part of this course is really used in all the different sciences. So with this, we already see really foundations of the scientific domain-specific applications because many of these have MPI codes, OpenMP codes, and with this, you will also see many people offer jobs in this area when we basically come to the next lecture and final lecture 16, where we review perhaps some job offers here in LinkedIn. So, of course, this brings you just to the beginning of programming these systems, and of course, scientifically with these different domains. Here, again, the idea is, of course, if you want to be a real expert in earth science or terrestrial systems, you need a couple of more courses, but at least you understand a little bit where the basically general idea relies in. Thinking about terrestrial systems and climate just as a stimulus again for you, I presented this praise report earlier. It is a nice way to see for you maybe where you have interest. If you are interested in HPC, one recommendation is don't maybe be only a general practitioner. Also think about if you can make a difference in a certain domain, right? For me, it's a little bit the Health domain and also, of course, remote sensing, where we use parallel and scalable machine learning. This is how I use HPC. And of course, being also general HPC professor, but having still my domain I publish in, I work in, and make contributions to science. Hence, this report is for you a very good source to understand that it's really used in astrophysics, in different ways of fundamental physics, climate weather sciences we do today. We had already life sciences with human brain, with basically systems biology, molecular dynamics and molecular life sciences. Energy research is a growing field, especially with batteries that we have seen also the last time in the molecular lecture or at the material sciences lecture. Then basically the whole aspect of manufacturing, engineering is really, of course, an important part. Computer-aided design, you have seen already ANSYS a little bit. That was also basically put forward by Reza, right? That aircraft and cars, everything is today created first in the computer with HPC and then developed in the real life. And you can go on, and even this report don't have all the different, let's say, scientific domains that we have, but I think it's a good start. And today we pick here the climate and weather, and here you can see what impacts it would have from, predicting climate change. We want to have better weather prediction, We have basically the ocean to be better understood with all its details, right? With wind, waves, tidal motion. And then you can dive in all the biochemical, basically processes, which means we want to understand why the Great Barrier Reef is getting smaller and things like that. So you see also where the challenge relies, the scientific case for HPC. You see many of these resolutions here is basically 10 kilometers when you do a large scale simulations over the globe. And of course, the idea would be, can we come to 1 kilometer grid resolution of global models, right? In other words, we want to make it much more fine-grained. We want to make it much more realistic and better understood. And with 1 kilometer scale, of course, the computing is orders of magnitudes more, but this shows also then the models can predict much more, right? And this can have directly better impacts, not only for science, of course, also for financial benefits for society and industry in different sectors. So hence, understanding our world is something which is very important. And hence, we are lucky that many physicists, of course, have done the job of really understood many of these aspects, but usually they study this very much in isolation to each other. So you will find that they're really expert in precipitation, like rain, for instance, or basically all the elements that you have is evaporation and the, let's say, energy interactions from the land surface. You can go on groundwater flow, subsurface flow, but the key challenge for HPC and terrestrial systems is, can we create models that have all these physical system changes together looked at? And hence, this is a very challenging aspect. And of course, in a way, something which really will motivate us probably for the next 30, 40 years to come to do perfect simulations. But many scientists have worked in that way to really come with this multi-physics approach, as we sometimes call that, to have really a much better reproducibility of all these models and really much better realistic scenarios when it comes to terrestrial systems. In order to do this, you can imagine that the problem of this dynamical system, when you have something like this, which changes really every nanosecond or so, heavily probably because you have lots of physical interactions, you basically come to the problem that you have a realistic part that you almost cannot really represent. So, and compute. So you need to have, let's say, from a verbal model coming down to a mathematical model that you concretely can describe over changes. And even if you describe now all the physics that are happening here, you would be quickly in a situation that you cannot compute this. It's too complex. So you have to assume some simplifications to the model. In one way, we know this already how that works. We go with numerical approximations in order to get basically to a better representation of this, which is computational feasible, because a real mathematical model or the real reality would be unthinkable to compute right now. Of course, we can think after exascale what comes, and also with quantum computing, we have new resolutions of optimization procedures, but still we are long away from really simulating whole process on the Earth perfectly. And still the ideas that we have inherent in this is, of course, a physical formula. So we are not left alone in all of this. And we are basically have this evolution over time now, and think about all the physical rules and equations that we basically luckily already invented, and can start then from there in order to basically bring this into these mathematical equations. And in order to do so, this numerical simulations, and this is now something which you have already seen here and there in some lectures. So it's just more or less a kind of repetition where we said it's basically applying definitions iteratively, right? Instead of having a closed form solution directly compute everything done, we do this over time and basically approximate a lot of things. And there are different questions that we want to go for. One, for instance, which is quite known is the equilibrium state can be to some physical processes where we have a so-called full stop, so that the state really doesn't change anymore, interesting enough. Or what we have often also in earth sciences can be to some form of periodic state, right? So that the state of the system returns over time. One broad example or coarse-grained examples of course, here spring, summer, fall, etc. Where you think, of course, after these periods, I come to the next spring and so on. So there's a certain periodic state in all of these different physical processes, but we have to identify and to understand them. And on some of them, of course, we find equilibrium states where we have, let's say, crushed the world too much and we cannot come back to any state. Let's say oil in the ocean or so, if we continue doing this on orders of magnitudes on the same coast, you can imagine this would be quite of an equilibrium state for some life living there. So there's no change anymore, everything is death. This is, of course, now an extreme example to make you aware of these different elements. But these are, let's say, example scientific questions why you do all of this. You want to understand, of course, the field phenomena. Then the way how you do this now is to use so-called PDEs. And this is something which also I think Reza introduced, I reused here and there in some lectures. In a way, it's basically the representation of this multidimensional dynamical system that you always have. And the good news is there's also really toolkits for it. One is PET-C, for instance, and they provide you basically with a toolkit around all the different basically formulas you require. Let's say on earth science, you can imagine, and the way around our world, we have sound, heat, fluid flow that was basically explained by Reza, but we have electrostatics, the molecular world we had already described. So here, of course, we have always these equations, which are in one way or another, this function of several variables that are changing over time. And the point is here that we really don't do this ordinary differential equations. If you know a little bit from math or back in your first, let's say, mathematical, steps, we did this, functions, and then we take a derivative. And usually we did this always on one single variable. So the key goal of this partial differential equation is now to understand the change from all of these different variables. That's why it's called partial differential equations. Right? And this is really a general method of HPC modeling. So no matter where you go, you usually have these PDE solvers, which are very much, of course, then also supported by toolkits. Now let us come to some concrete example. Obviously, there are many codes in the earth science domain around, and I picked this one here because I like it in terms of coupling real terrestrial systems and to make you aware what that really means and why we have to couple these codes. You see here a terrestrial system from a 10,000 feet perspective. So let's assume we want to basically simulate this box and we want to understand the basically complete flow of water in this box. Obviously, when we have a flow of water, this basically has different levels where water plays a role and which of course interacts with each other. If you think about, we have a subsurface flow, which is called here par flow. This is a code that is actually just dealing with the physics and the subsurface, right? So soil moisture plays a role, many different variables, but of course you can imagine that the groundwater modeling here in par flow is heavily dependent on how you do basically the land cover or the land model here, right? Which is a CLM. So it's another model that is actually deals with all the chemical processes and physical process of infiltration, evaporation, with different variables again. Hence, it also affects the groundwater of how much, basically soil moisture will be there after certain, rainfall, for instance. And then you come back to rainfall and other aspects in the atmosphere. Obviously, the rain has to come from somewhere, and the atmosphere has also other elements like clouds and so forth that, of course, will affect the land and also indirectly then even the groundwater. So here you come to a very complex problem of having variable interactions that on different levels interact with each other in order to form a real physical representation of this little bit of the Earth. Now, to even make it more challenging, we don't want to do this, of course, on a whole continent scale. In a way, it would be nice to really understand it maybe, on a partial area of land, let's say on the Reykjavik Peninsula. Right. So then, of course, you can imagine that the computing might be quite tough. You have a really detailed representation of the Earth in this part of modeling, and then have to basically compute all of these different physical models. So how you do this is basically you need interactions and then, of course, feedback back and forth through this model. And basically, you have also different scales, which means we talk about a so-called multiple spatio-temporal scale on these high resolutions. And that means these three codes don't really run completely synchronous. So we have to find a way to see how that really works, that they basically can run in parallel inform each other, but of course, maybe use a different number of cores, for instance, to have different timescales represented. And here's another representation of this. I just have shown that partly already in some other lectures, just to make you aware again. Of course, we jump down the idea of the whole area that we want to model into different blocks. That's what you already know. Here it looks almost like a Cartesian that you already know. And let's say we want to understand the flow of the river. Here you have a land surface model that we have as a CLM. Then we have the atmosphere Cosmo and the subsurface with path flow. And all of these codes are actually implemented by using MPI and OpenMP, all that you know, by basically doing this block 3D character of this essential ideas. When you now think about that, the river is actually going basically diagonal to a scene here, maybe through the Cartesian. You can also imagine that we here and there use more tree-like structures in order to represent this. Just to make you aware that now there are 3 codes that are using all the principles and practices we had learned in the first conceptual part for each other, right? So each of those is a full-blown code already that is running on a supercomputer. It's here basically illustrated a little bit, but what sort of missing, of course, now would be another code that is then responsible for actually exchanging all the arrays and all the physical variables with each other. So you would see here that the OASIS coupler fulfills this role using also the MPI COM world across all these different kind of codes that you have, right? And with this, you're basically then able to have the soil moisture informing the CLM. And with this, we already can steer the evaporation into the atmosphere. So it goes through these different steps, so to speak, through these different codes in order to really represent real physics that are happening. And OASIS is just one coupler. There are different couplers around. And in fact, when you do this now and analyze this, as you can imagine, this is already a very tough code representation. You see here Scalaska, what you already know from the performance analysis perspective. Here we see now that we essentially have 3 codes, right? We have the Cosmo code, the Parflow code, the CLM code, and you really need Scalaska for this. Another idea of saying what we conceptually learned is here represented, because before you had a processor distribution of 192 cores for Cosmo, 160 for Parflow, and 160 for CLM, but it was not working well. So after analyzing and tuning with Scalaska and see who is waiting for which, part of the system, which would be unthinkable now for a human to do manually. Hence, we have this automatic instrumentation that you learned, and by this you can analyze it, and by then see finally, oh, when we do here some changes, we can maybe do to other processor distribution as well, and then it runs much better. So here was a load imbalance again, as you see from the number of cores applying. And this, of course, helps them the study to run a perfect model. Another example, and how that looks like now in a video I have shown you here. I think this is some representation of these kind of codes that you see here. Of course, again, very blocky. Think about that we as scientists usually don't want a perfect representation like Unreal, right? Like look good in a game or so, but it's not really the realistic values. Here you have, of course, a scientific representation of this, where you see that the, let's say, soil moisture and the groundwater is actually coming up and forms then this interesting water area here that you see. And this is really time by time computed. You see here the cycle, right? Almost like in your assignment with the water and the boats. The same way is done here. We have always an iterative loop going over everything of all the physics. But what's happening here is now the PDE solvers are solving really the path flow and the groundwater modeling here over time. So, and this will be going, more and more. So I think the learn effect is then not really more. So I will stop here and continue maybe with the second part. Let me just go then to the climate models. So for climate, we have, of course, a situation that it's another very large area of basically earth sciences. Obviously, there's many questions in the future, but of course also of them which are very, let's say, apparent to us from daily life. And that's why I wanted to bring it a little bit to see that our numerical weather prediction models fuel your weather forecast you see every little day, right? And this uses, again, numerical methods that we learned before. It actually leveraged a lot of physical equations using the partial differential equations, which is not only the physics laws, it's also chemistry, of course. And also when we think about particles in the atmosphere, it also could be using the laws of motion, laws of fluids, and so on. And also what is often happening is that the characteristics of those models are also following, of course, a little bit this kind of grid structure that you also already know. Of course, it's loaded. The bigger you go, the vertical grid. So you can, of course, extend to the atmosphere, as we just have seen. And here have lots of different physical processes as an example. Or you are again on the, let's say, land surface interactions, which have, of course, also already quite some loaded physics. And to calculate that over time really requires supercomputers, which is good news because basically all our weather predictions here in Iceland, we have a Danish supercomputer that we leverage partly for this and these models and derive from this. So it's in the world already a real, let's say, network of systems which are very clearly giving every day the weather without any funding problems. So this is clarified with a lot of the Met officers. However, the problem remains that we have numerical methods and they are unstable, what you already noticed. So you will see that the weather prediction, everything which is predicted over, let's say, 3 to 4 or 5 days, is already starting to be a little bit, let's say, unreliable. And this is in the numerics. And of course, by having the grids better fine-tuned and have soon in the future also perhaps much more regional granularity of forecasts. I think some of the Met Office talk now in the future with research on the foregarden level, right? That is, of course, one of the driving requirements. But here we're seeking also to improve the weather prediction because now we know sometimes we don't know really if the weather next weekend will be as predicted or not. It could work, but of course there's a certainty that this will be not happening. And the reasons for this is unfortunately the idea of these numerical methods, which have lots of uncertainty inside and some instability over time, which is basically just approximate many ideas, as you know. That goes now back to my point that we don't really do a full-blown directly calculations of all these models. We do approximations. And these approximations, of course, on top of each other over many different days, then accumulate to more and more uncertainty that basically we really reach the predicted weather forecast, for example. So the same, of course, can be said about atmospheric models. When you think about a long-term solution, having, let's say, long-term climate research would be another one where you have different spatial solutions and scales. You have basically different equations that evolve over time and space. And so it's a quite complex area to do. And of course, you have many of these equations you have to think about from physics. Some of them are very much known, the conservation of momentum. I think that is clear for many of you that knows that the vertical motion basically is here considered. The thermal energy equation, the continuity equation, the conservation of mass. So energy cannot be lost, it just transformed and things like that. So this is basically different equations as just examples for you that are here and they're in fact primitive, right? So basically they're not so complex. The only problem remains that, of course, you have to consider them as a whole if you want to have a terrestrial system or a climate simulation. And that's where the complexity comes in. And hence, luckily, there's then the solvers, the PDE solvers in essentially high performance computing, which by now with PETSI and many other libraries have been really, performance optimized in many years now. So they're really optimized for high performance computing and helps a lot of these codes to be really on a high performance scale. Hence still to do more regional, kind of predictions, we could use, of course, more computing power again and again by adding more details, more models, or as I said in the beginning, more physical processes to make it really realistic. And here you see a parallel application example from a concrete parallel code. As I said earlier, this is an interesting code because it's actually based on Fortran. And it is a software package that has many different techniques. and a plug-in mechanism even. So you can have here, of course, model outputs for Typhon as their example, of course. You have polar models, which are here and there used actually from Iceland to predict better what's happening in, let's say, more north lying countries. So basically some of the models that are used are then using rather the polar version of it, but the fundamental physics are still in the normal WRF. Just several aspects are different in the polar. And when you now think how you would use it to really combine this now with data, you see that, of course, many of these things, when they are calibrated, because they need some initial values to start from, also don't have accurate data. And this is another idea why essentially these models also not always can be perfect, right? Basically, you see here an example when you want to perfectly simulate what's happening in the Westfjords. And many of you know the Westfjords are quite interesting in Iceland when it comes to weather, and changes can be done in 10 minutes time from perfect weather, and suddenly you're basically in a big rainfall or storm with wind. And you see here a little bit the challenges in this. The grid points, red dots here, are really measurement stations. So here we know exactly what the weather is right now because we have measurement stations, but obviously when you now think the WRF grid, the blue dots, right? So this is a physical grid we put over it when we want to simulate it with codes. It doesn't have the ground truth everywhere. So what we have to do here to make the physics work, you interpolate, you, let's say, again, approximate what's basically probably happening right now, and then you initialize the models already with uncertainty. And this, of course, over time comes to the fact that we have here also the problem. So in one way, we need better models, but on the other way, it would be also good to have better measurement station networks or better closer measurement network stations to really inform these models better. As in the, let's say, example of a weather, of course, because of course these models are basically physics dependent, but they're also data dependent, not only for their basically their check if they're really true. I'm actually talking about validation of these processes of these physics, but also then of course for inform them for so-called boundary conditions or initial conditions really where they start from. However, if you want to know more, I give you some basically interesting reports, a bit older here, but it doesn't matter. This was a wind study where the question was where to best put wind wheels in Iceland. So this was basically looked at also using the WRF code, and where you can imagine there are also interesting results where you put best basically the kind of wind wheels here in Iceland. Funny enough, because they tried to remove one of the wind wheels recently, because the company went bankrupt, so maybe they were not listening to this report. But on the other hand, we have also a nice demonstration of some German manufacturing, because lots of bombs were used to knock it down, the wind wheel, but it was still, staying strong, which was quite interesting to see. But that's just a joke remark here. You can imagine here is lots of research to be done to better understand our world and our basically weather. But we also don't start from zero. I think these models are already quite accurate for the next 2-3 days. Basically also because the world has learned to really interact with each other. We do data exchange a lot, global models, regional models. Also computing power is not anymore a question of policy really. Everybody has understood that this is needed by the society. So basically weather research and numerical weather prediction, these codes have really daily resources they can use. As a side remark, however, still there are challenges on the political level. You have seen maybe, or some of you know, that the European, weather forecast was largely driven actually from the UK, and as UK was actually not anymore going to the EU and participates there, we have to find a new. So ACWMF, which was basically the center of supercomputing in the past for European weather prediction and so on, and the key driver of all of these activities, is actually now finding new homes in different membership countries, which is another interesting effect of how politics sometimes actually affect us scientists in the modus operandi, which was a well-established way of doing it with the ECWMF in UK. And now lots of things have been, renewed. However, of course, the good news is that the codes, the scientific knowledge, and many of these people will also go and leave the UK then to the new headquarters of the European Weather and Research Forecast Center. All of this, of course, remains. It just shows you that politics sometimes also can influence quite substantially this very established way how we citizens use this without even recognizing this, right? So I think many of the taxpayers will not even know that this is happening right now. They just use a weather app. Anyway, coming a little bit under the skin, parallel applications before we basically come here to the final, representation and lectures. I just make here a smaller and faster walkthrough because this is all what you know already. You see, we have here the domain. If you look on the WRF model parallel application, we have exactly the idea of hybrid computing. We have a halo region. We have the MPI talking between different halo regions and different chop-down ways how you do the Cartesian. And inside we have the OpenMP, the shared memory programming, making it then essentially then, as I said, hybrid. And this is something which you now basically have here already as another example that we had already. Before you go to the next time step, you do firstly an halo update exchange, right? That you see here, basically this value that you have here in this halo region, you basically process in the loop before you start the next iteration shortly and send it over. We call that the halo exchange in order to have the neighborhood physics that you already know from our heat equation right in the room. It's the same principle here. Of course, when you want to go over the whole domain here of the Earth. Also here you have, because the Earth is a globe for larger models, nicely the periodic boundary updates that you already know from your Cartesian idea. So here we have the same idea of halos, of Cartesian. There are different ways how you basically transport some of these variables. This is not so important right now to understand the deep down details. This depends on which variables, but of course it uses elements that basically then have the same idea of having a domain decomposition that again has its patches and then smaller tiles, which are then rather used with shared memory, OpenMP. And on the patch level, you only do distributed computing in order to basically simulate the domain where the hybrid comes from, of course. Also for I/O, you can imagine ParallelNetCDF is here used. One of these, we had also HDF5, but NetCDF is quite established in the earth sciences and has some quite impacts here also in the idea of really doing, concurrent access to one file and not doing what we learned before, which is kind of a bottleneck to have basically all this basically collected by one and then written to file. What you rather want to do is parallel I/O. You rather write in different parts of one file directly from all these I/O processes. So hence also here, the WRF code really leverages parallel I/O, things you already learned in one of the lectures. And let us just finish with a 5-minute video. It's a bit long, but I think it carries a very nice way of understanding, again, what we do in earth sciences.
Climate and weather models are notoriously complex beasts. It takes a small army of scientists and computer programmers a year or more to build a model. Then they need a supercomputer fast enough to run it. Like those models, the machines themselves can be unfriendly. They're hot, they're expensive, they're big. But when you're trying to model major parts of the planet's climate, you'll put up with a prima donna to get punctilious power. But always in the back of your mind, a question. What if climate research had some more accessible tools? Like one of these, a desktop-sized supercomputer with climate models loaded and ready to run whenever and however a researcher needs it.
When I develop something I can run it, I can test it immediately, I can see the result. So it increases the productivity tremendously.
NASA's vision is to deliver a set of quality control procedures so researchers can perfect their own algorithms with a standardized baseline. The plan would essentially declare a minimum standard for climate and weather research, facilitating a rapid process of sharing and evolutionary development of new ideas, and a rapid transition from research to operation. Where big iron costs millions, these hot rods cost many orders of magnitude less. Where the giant systems require special rooms and architecture, desktops fit comfortably into ordinary equipment rooms or even office spaces. But perhaps most compelling is how these machines deliver turnkey systems, able to ingest data and start crunching shortly after installation. They democratize climate research, analogous to how ordinary personal computers democratized day-to-day computing tasks not long ago. In other words, easy.
The reason we put in a common software framework is exactly for the different disciplines to come in and use the same interface to be able to exchange data, exchange model, exchange workflow. So this is a box that for everybody.
NASA is one of the world leaders in climate model development. The space agency's new GEOS 5 model already produces highly detailed, tightly calibrated output. By facilitating heavyweight climate research on modest budgets, NASA hopes to open the door for wide groups of scientists to pursue dramatic climate research that might otherwise have been inaccessible. The agency's plan essentially gives away computational models to run on these systems, thus seeding the research ground with new opportunities for discovery.
This capability that's provided by such a system allows us to run models at a reasonable resolution for development. And then once we're satisfied with the results we're getting on the desktop system, we can then do production on our very big supercomputers that are room-sized systems.
NASA's software currently runs on Linux, but as these new desktop supercomputers are also capable of running Windows HPC, the space agency expects to deliver code compiled for each operating system. The modeling tools themselves are written primarily in Fortran 90, so the research community can expect to find themselves in familiar territory soon after power cords plug into walls. Climate in a Box, NASA's big idea for modeling big science. You too might have access to the whole planet, right on your desk.
So I think you have learned a little bit on this video, but don't get carried away that these little boxes from desktops are really doing then the big blown simulations. As the last speaker, C. Bloom, was actually alluding to, this is much more for experimentation of your algorithms, for small testing, for quick testing on established models. And when you really want to know if it makes a big impact, then you still have to use a big supercomputer to do the run full-blown production model. Hence, HPC is there to stay and cannot be just, exchanged with a couple of boxes. But of course, the complementarity of the approaches for small experimentation directly in a desktop computer in the future is, of course, something very powerful, and with GPUs also realistic. So with this, we have covered the last field of applications. I hope it was useful for you. And we actually close the course now with the final lecture 16 the next time.